In this video, we're going to look at Newton's third law. Please make sure that you've already watched the videos on Newton's first and second law, as understanding those will be necessary to understand today's law. Please start by completing these questions. Pause the video while you do that, press play once you're ready. You should have now done these 5 questions. Please pause the video to mark questions 1 and 5 and press play once you're ready. You should have now marked questions 1 and 5. I'm now going to go through questions 2, 3 and 4. So for a plane flying at constant speed and height, here's my plane. Don't bother drawing objects, just draw them as dots. It's flying at constant speed, so that means the forces to the right and left must be what? Say your answer to the video. You should have said the forces to the right and left should be equal or balanced. What's the name of the forward force on the plane? Say your answer to the video. You should have said something like engine force or thrust. What's the force against the motion of the plane? Say your answer to the video. You should have said air resistance. Now it's flying at constant height, which means that it's not moving up or down at all. So actually vertically, it's completely stationary. Vertically, it's not moving at all. It's only moving horizontally. So what can we say about the forces vertically? Say your answer to the video. The forces vertically must also be balanced. What is the upward force on the plane called? Say your answer to the video now. The upward force on the plane is called lift. That's a special force generated by the wings of the plane. And what's the downward force on the plane called? If you said gravity, that's not quite right. Gravity is a whole topic which includes gravitational potential energy, gravitational force, gravitational field strength. The force is called either the gravitational force, you can call it that, or you can call it weight. We usually call it weight. So there's the plane. For question 3, we need to do the object sinking in water. So we always have that downward force of weight. There will actually be 2 upward forces on the object if it is sinking. What are the 2 upward forces acting on the object if it's sinking? Say your answer to the video. So there'll be drag forces or water resistance, but there'll also be upthrust. Even though it's not floating, there's still upthrust acting on it. It's just the upthrust isn't enough for it to float. So there is still upthrust, it's just not a big enough upthrust for it to float, so it sinks. Finally, the calculator resting on the table. So it's resting on the table. So what can you tell me about the forces acting on it if it's at rest? Say your answer to the video. Well, if it's at rest, the forces are in equilibrium or they're balanced, or the resultant force is what? The resultant force is 0, and the 2 forces are weight acting downwards, and the force upwards, we can call it the normal force or the reaction force. I call it the normal reaction force. Normal just means at right angles to the surface. So let's say here's the table. The normal reaction force is at right angles to that surface. So we're now going to move to Newton's third law. The first thing I'm going to do is write down a statement of Newton's third law. So what is Newton's third law? Now, there's a common way which Newton's third law is written, which is this. Every action has an equal and opposite reaction. Now, I like how that sounds. I think it's quite poetic. And I think once you understand physics, it's okay to say Newton's third law like that, because it sounds nice, it reads very well. But I don't think that's very helpful the first time you're learning Newton's third law. So I'm going to put that in brackets, and I'm going to state Newton's third law in a different way. I'm going to say it with a lot more information. So Newton's third law says that every force interaction between 2 objects or 2 bodies, these could be solids, liquids, or gases. So every force interaction between 2 objects is made up of force of object A on object B, and an equal and opposite force of object B on object A. Both forces are of the same type. So what I mean is, whenever we have a force, that is an interaction between two bodies, between two objects. And if there is a force of one object on the other, and I'm calling those two objects A and B. So if we've got object A and object B, and object A is exerting a force on object B. So let's say these are magnets and A is repelling B. So this here is the force of A on B. And as you can see, it's to the right. It's a magnetic force because these are two magnets. So when A exerts a force to the right on B, B exerts a force of equal size but opposite direction on A. So force of B on A. And it's also a magnetic force. So we've got two forces acting on two different objects in opposite directions of the same magnitude and of the same type. So I'm going to say that again. These two forces, one acting on object A and one acting on object B, are the same type of force. They're the same magnitude, but they're opposite in direction. And this is true every time any two objects interact. So it's true whenever there's a force. You never get a force by itself. Every force comes in pairs because it's always an interaction between two objects. Now, the best way to investigate this further is to look at some examples. The first example we're going to look at is an object resting on a table. So pause the video and draw the free body force diagram for an object resting on a table. You should have now drawn the free body force diagram for an object resting on a table. There is a force down, which is the weight, and there is a force up, which is the normal reaction force. Now, this is not Newton's third law. This is two forces. They are opposite in direction. They do have the same magnitude, but they're acting on the same object. Newton's third law is about the force on two different objects when they're interacting. These two forces are both acting on the object on the table. Let's say this object on the table is a ball. So this here is a ball. This normal reaction force is the force of the table up on the ball. And this weight force down here is the force of the earth pulling down on the ball. This is just a contact force between two objects, or a reaction force, and this here is a gravitational force. Notice both of those forces are acting on the ball. So this cannot be Newton's third law. Remember, Newton's third law involves object A exerting a force on object B, and object B exerting a force back on object A. Here, there's only the ball. So this is not Newton's third law, and it's a very common mistake. People think this is Newton's third law because these forces are equal and opposite, but it's not. Newton's third law is something different. If we think about this force, the Newton third law pair for that, what we call the Newtonian pair, is, imagine we draw a force diagram for the table. The table will feel a force of the ball down on the table. That force there, this one here, the ball down on the table, is the Newton third law pair for the table up on the ball. That is a Newton third law pair. Notice it's on two different objects. So you've got the force of the table up on the ball and the force of the ball down on the table. Notice it's the table up on the ball down on the table. The directions are different as well. One's up, one's down. Let's now do the same thing, but for the earth pulling down on the ball. Pause the video and say what you think the Newtonian pair is. What is Newton's third law pair for the Earth pulling down on the ball? You should have now paused the video and said what you think the Newton third law pair is for the Earth pulling down on the ball. So let's consider the Earth. Let's think about the Earth. So from the Earth's perspective, so here's the Earth. The Earth actually gets pulled up by the ball. It's the ball pulling up on the Earth. And that will also be a gravitational force. I'm going to circle that Newtonian pair in green. This and this are a Newtonian pair. Notice two different objects, the Earth on the ball. The Earth pulls down on the ball pulls up on the Earth. That's a Newtonian pair. Two different objects, two different directions. People find this a bit odd. They say, well, how can the ball be pulling up on the Earth? Like, the ball falls to the Earth doesn't fall up to the ball. But actually, the forces acting on the Earth and the ball are absolutely equal in magnitude. Why do you think it seems like the ball falls to the ground, but the ground doesn't fall up to the ball? Why does it seem like the ball falls towards the Earth, but the Earth doesn't fall up to the ball? Pause the video, say your answer, press play once you're ready. So the correct answer for that is, well, the Earth has a crazy big mass, 6 with 24 zeros kilograms. That's a really big number, 6 million billion kilograms. Whereas the ball might weigh a few hundred grams. The mass of the Earth is so big that the effect of that force is much smaller on the Earth. The mass of the ball is much smaller, so the effect of the force is much bigger on the ball. But the force that they both experience is the same. The force of the Earth pulling down on the ball, this one over here, sorry, is equal and opposite, equal in magnitude to the force of the ball pulling up on the Earth. Let's move to another example. A person walking along. So actually, the whole way that a person walks along the ground, so if this is the person's foot and this is the ground, what the person does is they push on the ground. So this is the foot pushing back on the ground. What's the Newtonian pair to that force? Pause the video, say your answer, press play once you're ready. You should have said that if the foot is pushing back on the ground pushes forwards on the foot. So again, notice you've got two objects. You've got the foot and the ground. This force is the foot pushing back on the ground. This force is the ground pushing forwards on the foot. Notice the directions are opposite. This one is pushing back. This one is pushing forwards. And they are the same type of force. They're both contact forces. So that's how all things move. This can also be applied to bicycles and cars and planes, anything where they push back on something in order to propel themselves forward. You could think about yourself swimming. You push back on the water and the water pushes you forwards. That is an example of Newton's third law. Next example, a floating object. Pause the video and draw the forces, the free body force diagram for an object which is floating. Press play once you're ready. You should have now drawn a free body force diagram for a floating object. So the forces on a floating object are weight downwards and upthrust upwards. Now, if it's floating, those forces are equal and opposite. Is that Newton's third law? Yes or no? Say your answer to the video now. Hopefully, if you've understood the previous examples, this is not Newton's third law. Why is this not Newton's third law? Say your answer to the video now. This is not Newton's third law because this is a free body force diagram. This is all the forces acting on one object. These forces happen to be equal and opposite because this object is in equilibrium. But they could very well not be. So you could think of an object where the weight's bigger than the upthrust, and that would sink. It just so happens that here the weight is equal to the upthrust, but this is nothing to do with Newton's third law. This is just an object where the forces are balanced. Some objects, the forces are balanced, some objects are not. This is not Newton's third law. So what we're going to try and do is find the Newtonian pair for each of these forces. So we've got the upthrust, which is the force of something up on something. Pause the video, write down what you think those blanks should be, press play once you're ready. You should have said that the upthrust is the force of the water up on the object. I'd like you to do the same with the weight now. So it's the force of something down on something. Pause the video, write down what you think, press play once you're ready. You should have said it's the force of the earth pulling down on the object. So both of these forces are on the object. This is a free body force diagram. This is not a Newtonian pair. But what we're now going to do is try and find the Newtonian pair for each one. So I'd like you to please write down what you think the Newtonian pair for this force is. Pause the video while you do that, press play once you're ready. You should have now written down what you think the Newtonian pair for the force of the water up on the object is. The answer is that it's the force of the object down on the water. Once you get the hang of it, it's quite straightforward to do because you just swap the two objects around and change the direction. This one was water up on object, so the Newtonian pair is object down on water. Let's now do the same thing for this force over here. The force of the earth down on the object. What's the Newtonian pair for that force? Pause the video, write it down, press play once you're ready. You should have now written down the Newtonian pair for the force of the earth down on the object. So the Newtonian pair is the object up on the earth. Those forces will be equal in magnitude, but opposite in direction. They'll also be the same type. What type of force is the force that I've done in green? Say your answer to the video. It's a gravitational force. Let's do one more example. Two objects colliding or exploding apart. So let's say you've got two objects which are exploding apart. So let's say you have a gun and a bullet. I'm going to draw a very bad diagram of a gun and a bullet. So when that gun pushes the bullet out, the gun exerts a force forwards on the bullet. So this is the force of the gun forwards on the bullet. What will be the Newtonian pair for that? Pause the video, write it down, press play once you're ready. You should have now written down the Newtonian pair for the force of the gun forwards on the bullet. The Newtonian pair is going to be the force of the bullet backwards on the gun. We actually call this recoil. When somebody fires a gun, for example, if you ever go play pigeon shooting or paintballing, when you fire the bullet, the gun also pushes back towards you and it can actually hurt your shoulder. And that's because of Newton's third law. If the gun exerts a force forwards on the bullet exerts an equal and opposite force backwards on the gun. So that's an example of an explosion. We can also think of an example of a collision. So imagine you have two balls, one which crashes into the other. So let's say you're playing snooker and one ball hits the other ball. So there's ball one, here's ball two. So if ball one hits ball two, so let's say ball one is moving to the right and hits ball two. So at the point when they collide, so just when they're touching, there is a force on ball two and there is an equal and opposite force on ball one. So this over here is the force of ball one on ball two. Notice it's a force to the right. What will be this other force that I've labeled here? Say your answer to the video. You should have said it's the force of ball two on ball one. And what that means is if two objects collide, they exert the same force on each other. Now, in this case, I had two balls which were the same mass, so they'll have the same effect on each other. But let's say one of these objects was way heavier than the other. So imagine, for example, that a lorry crashes into a car. Well, the lorry has a much bigger mass, but when the lorry crashes into the car, the force that the lorry exerts on the car is equal to the force that the car exerts on the lorry. So if this is a lorry and this is a car, the lorry crashes into the car, the force they exert on each other are equal and opposite. So this is the force of the lorry on the car, this is the force of the car on the lorry. They are equal in magnitude. But which of the two objects is going to be affected more by that force? Say your answer to the video now. The car will be more affected by that force. Why will the car be more affected by that force? Say your answer to the video now. The car will be more affected by that force because the car has a much smaller mass. Now, if we look at that a bit more as an equation, F equals ma. What that means is, as we've seen already, the acceleration is directly proportional to the force. So if you're not familiar on this, please watch the Newton's second law video. And the acceleration is inversely proportional to the mass. Now, if I'm telling you that the lorry and the car exert the same force on each other, that means this is a constant. That's not changing. So the force is a constant, that's the same for both. Now, if the force is the same for both, but acceleration is inversely proportional to mass, the one with the bigger mass is going to have a smaller acceleration. And the one with the smaller mass is going to have, finish my sentence, a bigger acceleration. So here, the car has a smaller mass, so it's going to experience a bigger acceleration, whereas the lorry has a bigger mass, so it's going to experience a smaller acceleration. So to summarize that, they both have the same resultant force acting on them, because the force of the lorry on the car is equal in magnitude to the force of the car on the lorry. Those forces are in opposite directions, but they are of the same magnitude. But that force affects the car much more because the car has a much smaller mass and will therefore experience a much higher acceleration. Please now do these 4 questions. Pause the video while you do them. Press play once you're ready. You should have now done these 4 questions. Please mark your work. Pause the video while you do that. Press play once you're ready. Here are the answers to B and C. Pause the video while you mark. Press play once you're ready. You should have now marked these 4 questions. Please try these questions here. Pause the video while you do that. Press play once you're ready. You should have now done these 4 questions. Mark your work using these answers. Press play once you've marked question 5A to D. You should have now marked questions 5A to D. Please now mark the rest of questions 5 to 8. Pause the video while you do that. Press play once you're ready. You should have now marked these questions. Please now do these questions. Pause the video while you do that. Press play once you're ready. You should have now done these questions. Please now mark those questions. Pause the video while you do that. Press play once you're ready. You should have now marked questions 9 and 10A and B. Please now mark these questions here. Pause the video while you do that. Press play once you're ready. You should have now marked these questions. And that's it for this video. So in summary, Newton's third law, what I will often just refer to as N3. The fancy way of saying it, the poetic way of saying it, is that every action has an equal and opposite reaction, but it's much more clear to say that whenever 2 objects interact, the forces they exert on each other are equal in magnitude and opposite in direction and of the same type. Newton's third law is always about an interaction between 2 objects, and the force of A on B is equal and opposite to the force of B on A. I hope this video was useful. Please like and subscribe to watch more videos on GCSE physics.